My name is Guillaume Chevalier, and I'm working at Neuraxio as a machine learning expert. And same goes for Vincent Antaki, who's there with me as a data scientist, machine learning specialist. So, what is Neuraxio? We are the AI startup backing the other AI startups. So, we enable AI for tech businesses, building AI products and AI assisted services. So you can visit our website afterward. And let's get technical. So this is a technical talk. First, Naraxio. What is Naraxio? It is our open source machine learning framework. And we've built this machine learning framework out of business needs. And it is also very good for research. Research is so complicated these days with machine learning and deep learning algorithms, trainings, hyperparameter optimization. We'll get into that to see how to make this more clean. So we've put a great emphasis on pipelining, so pipeline design, modularity. In fact, everything in Neuraxio is a step, whether it is for data pre-processing, whether it is your model, post-processing, or some operators such as for loops and stuff to play with your data along the pipeline. Everything is a step. It is like a component in user interface design that you might know, such as Vue.js or React Native, for instance. So Naraxio is a full-blown machine learning library that can really complement your stack. So it also includes automated machine learning, which is the art of finding and picking the best hyperparameters for your models. So this known, it is compatible with TensorFlow, scikit-learn, and most, if not all, of your favorite Python machine learning frameworks. So it is compatible. And finally, we've also put an emphasis on making it easy to transition to production. So what happens with most research projects? Well, they hit a wall once the research is done. You probably did not cared about the licenses, or maybe your algorithms are really just too crappy and one way, just giving results and not clean enough for putting into production. So we'll see how to structure things properly so that your project from research to development to production is good. So automated machine learning. It is really the art of choosing and picking the best hyperparameters for not only your model, but amongst many models. So it includes the whole pipeline from data preparation, pre-processing to post-processing of the data and stuff like that. So everything in your pipeline can be configurable. The data pre-processing algorithms, such as your sampler, if you have data imbalance and stuff like that, you can parameterize them and optimize them as well. So here at the right, we can see a chart. So basically, as you increase the quantity of data, well, you also could probably get more performance out of your predictive algorithm if you use a more complex model, such as a deep learning model. And this is the biggest, if not the biggest, well, one of the most important question when choosing a machine learning algorithm, and it is very hard to answer. Every data scientist ever will reply to you if you ask them the question, oh, what should be the model given this quantity of data, and is it feasible? Well, this is a very hard to answer question, and it is here that using different model sizes, different hyperparameters and stuff like that can be really a good way to solve a machine learning problem given an automated machine learning algorithm, framework, and a way to structure objects. So here's a little introduction to hyperparameter search strategies. And for the people here that might not know what hyperparameters are, well, it is like the genetic code of your artificial intelligence algorithm. So you can choose the learning rate, the number of neurons per layer, stuff like that. And usually we search this with a grid layout. It is the very most basic way to do for instance, in scikit-learn. So you have here in 2 dimensions 2 hyperparameters, and in blue are the good regions, and you would like to find and try to train your neural networks with 2 hyperparameters in the blue region to obtain a good score, because this is where you would obtain a good score. And as you see in the grid layout, you might not every time find the best hyperparameters. However, if you try the same number of trials to train your models with different hyperparameters and to evaluate their score on the validation set, then with the random layout, with the same number of points, here 9 points, you will explore your hyperparameter search space much more, let's say, widely and wildly. So there are better hyperparameter search strategies than random search. One of them is the tree parson estimator, the TPE, and we've coded it in Naraxio and made it available to you guys under the Apache 2 license, so that you can actually not only find randomly your hyperparameters one trial after another, but you can have an actual good hyperparameter selection strategy that will pick the next best one to try intelligently.
All right, so this is where I come in and do the fun part. I'm teasing you, Guillaume. We're going to have a look at a practical example of time series processing. Now, as a disclaimer, I want to tell you guys that it's a fairly simple example. The reason is that we only have so much time to present it, but in small things come nice events. Anyway, so we're gonna look at time structured data. What are time structured data? Well, to make it simple, we're gonna start with 3 dimensions. The first one is the sample dimension, which refers to an individual training example. For instance, if you use a mini batching, then it's going to be your batch size. If you use the full data set in one shot, then it's going to be the size of your data set. Fairly straightforward for any person that played with data before. Samples. The second dimension is going to be the step dimension. In our case, since we're dealing with time structured data, it's going to be time step for most of it. So what are time step? They're tick-off time. This is what determines how long in time each of your samples are. But have an open mind about it. It could be a 30th of a second when it comes to signal processing. But if we would be in a natural language processing setting, then the time step would be more associated with a character, a word, or a sentence. It defines some kind of regularity in time. And the third dimension we talk about is the feature dimension. Features are simply the information we have about each time step. For example, in natural language processing, a word could be represented by 300 features using word2vec. In case of signal processing, it would be the actual signal values. So for instance, let's pretend we have 3 signals coming from an accelerometer. So you'd have X, Y, and Z signal from that accelerometer measurement. This means that you would have 3 features sent at each time step for each samples, and that these reading would be repeated along those axes. So we use the Rubik cubes to show you, to help you conceptualize 3 dimension of data. That being said, features could be themselves multidimensional. So for instance, applications such as video processing, where the video you have each is made of images, images which have 3 dimensions, so the width, the height, and the channels. So that would give us 5 dimension for video as a time structured data. But we'll keep it simple for example and use only 1 feature dimension. So the task at hand, we're going to be looking at the human activity recognition data set. where we want to classify the type of movement from phone sensor data. So our features are going to be, we're going to have 9 feature dimension, from the gyroscope and the accelerometer. We're going to do many-to-one prediction, which means that we have measurement at a certain frequency, which, if I remember correctly, is about 50 measurement or 30 measurement a second, some along those lines. Every sample are going to be 2.56 second long. So that's going to give us this dimension here as an input. What we're trying to predict is whether the user is walking upstairs, walking downstairs, sitting, standing, or laying. I don't remember the exact size of the data set. It's a couple 100,000, I think, 200,000 samples approximately.
This is given mini batches of 128 time steps per sample and 50% overlap between the windows of how the signal has been cut. And there was something like 30 participants, and I think 26 of them were in the training set, and the rest was in the evaluation set. So I would also like to comment before continuing, Vincent, for the people out there not familiar with machine learning nomenclature, I just want to point out that the X's and Y's we see at the left of the screen are like X's as the input of the machine learning algorithm and Y as the output of the machine learning algorithm, and that those X's and Y's there at the left of the screen are completely different from the X's and Y's at the right of the screen, where those are 3D coordinates, as in X, Y, Z, an acceleration in 3D space. So that is the only thing I wanted to add. I'm just realizing on the spot that we hadn't made that clear in these slides. You can go again.
Sure. Well, thank you for this clarification, because I would have skipped over it. So without further ado, we'll go have a look at the actual code and the actual example we had. And we're going to skip over that part because that's just what we presented. That's a video of how the sample collection was made. We won't go too much into data. That's the same picture. So just to make it already, I'm going to restart and run all so that's going to be done. And if there's ever some slightly slower part of code, they're going to be done, and we're just going to go scroll through this together. Actually, we're going to skip the loading dataset part, but because that's not very important for what we're trying to show. So how would you code this in an ML project using scikit-learn? So to start with, we'll quickly go over the kind of features we're going to use for this small example. Since we won't be using LSTM or any kind of recurrent models for this example, we need to find some intelligent way to reduce the time step dimension. The reason we're not using recurrent model in this case is that they would be overkill for this specific data set, and they take a bit more time to train, more than we have at the moment within the scope of this presentation. If you ever want some more information about LSTM recurrent network, Guillaume has some fairly good tutorial about it a bit all over the internet. You can just find him on LinkedIn or YouTube, and you might see this information, his talk on how to train recurrent neural network. So features. Since we need to reduce that time step dimension to meaningful features, we're going to do two things. First thing is we're going to use fast Fourier transform to take the whole sample and derive some, extrapolate some useful statistics about the frequency of that sample. I'm not going to go in details of how fast Fourier transform work, because that's a content for a full-blown math class, which we we won't go too much, which we don't have time for. But anyway, we do fast Fourier transform, which has a sliding with a sliding window on the data. And from it, we derive some statistic about magnitude and peaks. And we're going to take the data again and just compute mean, median, min, and max on it. And we're going to use that to collapse that time axis. So we do that. We take our input, we featurize it, take a decision tree, fit it, and then we're going to use our test set to see what's our current score would be. So our sklearn pipeline code does 85% classification on previously unseen data, which is not bad as a start, but this data set is fairly easy. So that being said, how would we code a similar pipeline but cleaner using Naraxio? And what does Naraxio give us as an extra for tackling this problem? So to make ourselves a cleaner pipeline, we'll define for each of our transformation as a step. Defining our pipeline in terms of steps allows us to implement separately the behavior on fit calls and transform calls. In our present case, though, we only need to define a transform behavior. So this is essentially the same processing function which we've had defined earlier, but they're defined as steps. Now, these steps, they're non-fittable, but one could conceive a case where you would need to derive some information from the data before applying a transformation, and that step interface which we use does allow us to do it if ever needed. That being said, we will use this fit interface. Well, under the hood, it really do use this fit interface when wrapping these sklearn model. So that's the next step. Once we have these pre-processing step defined, we'll define a set of classifier and their respective hyperparameter space to explore. So we have this sklearn wrapper that's built in Naraxio. This is an sklearn instance, and then for each of these, we define an hyperparameter space, which is the space we'd like our AutoML algorithm to explore. One important idea behind Naraxio is that each step self-define its own hyperparameter space, and this allows us to use proper code encapsulation. Of course, the full hierarchy of hyperparameters is accessible from the root of the pipeline. So in that sense, we're not losing this data. We're actually organizing it and making it self-encapsulated, which is good for modularity and code reusability. So we're going to define these five basic classifier from sklearn, decision tree, extra tree, ridge classifier, logistic regression, and random forest. We now have all the pieces to define a proper Naraxio pipeline, which is going to look like this. So we have the pipeline. We have here some train-only wrapper, which is going to print, which has a printer shape printer step. This is solely for making it the example clear. That being said, we could also add a proper logger call, which would log it into our log file, which would be a bit better than using the printer here. But we're in a simple example. We're not going to go overboard with all the fluff that comes with Naraxio. So we have a feature union, which is going to take the data and copy it, not essentially copy it, but it's going to pass it to all its component here. So all these one, they're all going to receive the same data and apply a processing on it, and then the feature union is going to concatenate their output. So really see this pipeline as the path the data is going to take, and then here we have a choose one step of, which defines an hyperparameter itself, which is which one of its children step is going to be used. So every time we sample an hyperparameter, we sample the hyperparameter from this whole pipeline, then this step here is going to define one children to be used. So essentially, this is very similar pipeline from the what we had in with sklearn, except here we can just choose sample a different classifier each time, and each one of them has its own hyperparameter space. Now, that being said, we could add some more stuff in this pipeline. We could add feature selection. We could add some more pre-processing. We could do ensemble method down here. You know, there's plenty of things to be had, but time is of the essence. So we'll go straight to the AutoML loop here. An AutoML loop is basically defined by a pipeline, an hyperparameter optimizer, which in our case, we're going to use random search hyperparameter. But as Guillaume said, we have a tree parson estimator, and if you ever want some more Bayesian approach, we have a validation splitter, which is going to take the training training data and split it between train and validation. We have a scoring callback, which defines the main metric our AutoML procedure is going to be monitoring, which will allow us to choose the best model afterward. So we're going to be choosing the best model based on which model had the best validation score on that specific metric. We could add some other metrics, using the callbacks function here. We have metric callbacks, which we could define here, and we can define a whole list of metrics which you want to monitor during training, even if you don't want to do anything about it. We're going to do 10 trials and only one epoch, because all these models we've defined are only do one fit over the whole data set, though it's entirely possible to use mini batch and have incremental model. That's a very important part of machine learning, and it's not left out of the framework, only left out of our example. And last thing we need, but it's a very important part, it's the hyperparameter repository. Basically, this is where we're going to be storing the hyperparameter we have sampled and the metric that comes with the trial that's been run with these hyperparameter, as well as the trial status and a few other things which I'll spare you the details of. That being said, this one is in memory, but we could have a one that is based in JSON, which is going to be stored on your computer, which would be something you might want to do if ever you don't want to keep all that in memory, which I think it's a good idea if you're running a project to keep some results on disk and not only in memory. Anyway, we do a fit here. And while our framework, while our AutoML loops run, it's going to be sampling, and you can see here that's the logger. That's the logger output, which we're putting here, which we're showing here, which is going to be monitoring, sample the various hyperparameter samples, of every trial, and it's going to be printing every metric we measure at every epoch. We only have one metric in this simple example, so we only have main, train, and validation. Main being referring to what you use as a scoring callback. If you had metric here, you could actually give them proper name. Only the scoring callback is called main by default. So this is going to be running for. It's actually very quick to run these 10 trials. They take maybe a minute. But we're going to be running and logging it. If you'd be using the hyperparameter JSON repository, then these log would be on disk, and you'd have them separated by trial. So we've did train these one. We've picked up the best model, and we're testing it, and boom, we got 93.5% accuracy on this data set. Incredible. What hyperparameter exploration can yield us. I hope I didn't use all that time, and I'm going to give you back the mic, Guillaume.
Hey, hello again. So, like me, you've probably been really blown by the results. This took, like Vincent said, like 30 seconds to a minute to run. It's amazing. In the previous years, I've spent hours optimizing for projects like this, and I've published papers. We've once tried, sequence to sequence models, not actually many to one models that were based on RNNs, but were bidirectional, stacked with residual connections, and we were getting with these kinds of model approximately 94% accuracy, and these classical models with data like this can reach an accuracy very, very, very close to that, and it's very so easy to build machine learning pipelines like that. It's amazing. So we could use the same design patterns and code structure to code other kind of pipelines, such as sequence to sequence, LSTM RNNs, GRU RNNs, UNets, and things like that. We could use classical machine learning data pipelines as well as we've presented right now. We could also mix different data sources into the pipelines, such as images and time series and natural language processing all at once in the same project as data inputs as x's to predict some y's or stuff like that, predicting many y's or things like that. We can really play with flexibility here with Neuraxio. And above is an image of different types of time series processing problems we can solve. So we've just solved a many to one type of time series processing problem where from left to right are represented time steps, which are like reading one from the sensors, reading two from the sensors, reading three from the sensors, and in the present exercise we'd have 128 time steps per sample at 30 hertz, so 30 readings per seconds. And well, here predicting in the many to one only one output in green, which is the classification of what is the movement among the six classes: walking, standing, running, etc. So there are some tasks that are one to many, only one input information to predict many output variables over time or over something different, as Vincent said earlier, that could be words in a document. And there is also many to many when you want to do forecasts and stuff like that. Many to many could scan, as in the first many to many we see at the middle of the screen, many past readings, and then hit the present moment and generate many future readings. That can be some auto-regressive problems like autoencoders as well, in the way the data is reshaped and trained as an unsupervised problem rather than a supervised problem to generate something out of the data itself. There are other many-to-many problems like the other one at the right, where as for every data input you have at every moment, you want an instant classification. So things like that can be done with Naraxio quite easily. Note that we've also built an event forecasting solution. This one is not public. We've put in a lot of time developing that. And if you think this is interesting for your business, for instance, well, that could be very interesting to talk about this. Well, here what we're doing is that as a time series, we have from left to right here some transactions. So the dotted line is the present moment. So what is at the left of the dotted line is the past. So we have three transactions here. One would be machine served strong coffee, another would be machine served light coffee, and then strong coffee again. And we'd hit the present moment with some time deltas between every past event. And we want to predict two things. So for every possible action in the future, whereas it could be serving light coffee, strong coffee, medium coffee, something else, well, for all of these three actions we'd have that would be possible, which one would happen. So and for every of these actions, so what is the probability of this action happening in the future? What is the likeliness to of this happening? And we predict a second variable for all of this, which is the time delta. So if it was going to happen, if the probability of happening was evaluated to true, well, when would this happen in the future? So this is the kind of thing that we predict, and it can be very interesting for predictive maintenance, or for instance, predicting the actions of some customers, or recommending some products to buy for recommendation systems. The applications of this are wide, and we haven't seen much people predict things in this way. In fact, we've even got around a patent to build this by not infringing other people's previous work, and we found a way to do it in our own way, our own novel way. So that's very cool. In conclusion, with Neuraxio, you can separate everything into different abstractions. So, as we've seen in Vincent's demo code, we can do some data loading at the beginning, and then we can do data pre-processing in different classes that could be like NumPy max, NumPy min, fast Fourier transform, and then concatenating all of that in parallel, and then merging the data that is refeaturized and with a dimension in less, that would be the time series dimension reduced to simple static features for the classical machine learning models, for instance. So you could do almost anything with 5D data, 3D data, 4D data. You can mix different data sources into this. It's very flexible, and you can define your models separately from your data preprocessing. And finally, you can tune everything at once. And if you really would like to do this, you could have an automated machine learning loop inside an automated machine learning loop if you were to have a problem in which you would compose different algorithms using different data sets, for instance. Everything could be done with this. So this is good for research, to keep your things clean and easy to tune. It is even better for business, as your research project will not hit a wall once it's done, having the good abstractions for reusability and for deployment, and not depending too much on the disk and stuff like that. And it's also very good for writing tutorials that have you just seen today, right now. So yeah.
Right. I don't have much to add to this, only that you've only seen a fraction of what this framework can do. We've have so much time, but there's plenty more under the hood, and it's worth it to dig into it and see what it can do. Yeah.
Yeah. So this is a quick overview of our website, the kind of services we offer. So first, well, there is coaching. If you want to build your machine learning project in your company to move things forward, often our clients already have hired some interns and employees and have failed for years. No, that's a joke, but it it can be seen. And this is a sign you should do business with us, because we like working with teams and really getting to the point of making your project work. Well, we could offer services. We have the event forecasting product. We have some technical trainings, and stuff like that. So thank you very much, and don't forget to connect with us after the talk. You can connect with us on LinkedIn. You can write to us. You can visit our website to book an appointment or see more stuff that we do. We also have a lot of things on GitHub and on our blog. Thank you very much, and we hope you've learned a lot of cool things, actually, that can save you time when building machine learning pipelines and projects.
Somebody has asked, is it possible to have a set of the code that you guys were talking through before?
Yeah. So basically, this example is already online, but we've just updated it recently. So you could find it right now, the old version, not the new version you've just seen today. The old version is on the GitHub of Neuraxio. So you can Google Naraxio GitHub and go on the GitHub and find the example that is called Clean Kata, Kata, as like a some kind of exercise.
Karate.
So yeah, karate exercise as a something to get you warm. And well, we'll also update soon the example on the official documentation website of Naraxo, naraxo.org. So it will be there in the table of content soon.
Does hyperparameter tuning result in overfitting of data? If so, how do you avoid this?
Very good question. So you basically want to have not only a validation data set on which you pick the best model, but you also want to have a test data set on which you test your model and measure its score as well after having picking the best model. And you really hope that the validation score was the same as the test score, and this is the proof that your model, well, you weren't just lucky picking your model in the validation phase where you train different models in the AutoML loop. So this is one thing, and doing that, you want to ensure that your validation set distribution is the same as your training and no testing set distribution. So this means you would have one test set that you would split into, let's say, 80% for the validation and 20% for the real test at the end, and you would optimize the automated machine learning loop on the validation set. So with enough data examples, you wouldn't really see the difference between the pick of the best model and the test at the end. And also note that you also really need to have data that fits with your real life scenario you would like to solve, because models selected with automated machine learning as such uh, can sometimes not generalize properly if you apply them to data that is not like your environment in which you picked your best model. So be sure you have real life data, that is data of your real application that you intend to use, because otherwise you might not pick the best model at all.
Does this framework support multi-class classification problems as well?
I'll take that one,
Yeah.
Guillaume, if that's okay
Okay.
with you.
Good.
I just want to do at least one of them. So yeah, of course it does. As if you remember the part where I presented the IPython notebook and the AutoML loop, the only thing you have to define, you have of course to have a pipeline that does your prediction, predicts the output of the right shape for what you want to do. And the only thing you need is to put the proper scoring metric. That's as simple as that, and you can define a pipeline for multi-class classification.
When we should use time series deep learning methods instead of regular regression?
Well, I've explained this in the beginning of the talk, but I haven't detailed enough the figure, I think. So, Vincent, could you show again the figure where there is the art of selecting a model? We can see here that we have the deep learning model in blue, and it is also the one that achieves the best performance. However, to get performance like that, you need a huge quantity of data, and this is relative to the complexity of the problem you're trying to solve. It is relative to the quality of your data, and there's probably a signal to noise ratio in your data where some data examples could be crappy and just be noise, and other ones would be real signal for your algorithm to learn. So this also accounts for the quality, and there are so many different techniques and ways and to format data and to measure it and to process it. So it's really a hard question. But the thing you can know here is that if you have a small quantity of data, well, a machine learning model might perform way better than a deep learning model. So, for instance, if you have, let's say, only like 1,000 documents on which you want to fit something, you probably would like to use some machine learning algorithms or a very small neural network rather than a deep learning algorithm if you don't have access to a pre-trained deep learning algorithm, for sure. Because if you can train on more data, then you have more data. Let's say you have Wikipedia or something like that, right? So that being said, the choice can be hard, and it is worth exploring different techniques, especially if those techniques are already built into let's say scikit-learn or TensorFlow. Well, it's quite easy, as you've seen in our technical demo, that and not only that, but combining machine learning techniques with deep learning techniques in your machine learning pipeline that is optimized automatically with AutoML. Well, you're making your algorithms proof to the differences in quantities of data, which can be very interesting if, let's say, you're a business doing machine learning and you have different clients having different data set sizes and you need to retrain on different data set sizes. I've seen this problem again and again and again in my consulting, and it's very good in those cases to use automated machine learning to avoid having to tune everything from scratch again for your different clients.